Welcome to the MCAT Basics podcast, brought to you by the physicians at Med School Coach. Each week, Sam Smith breaks down high-yield MCAT topics so you can score as high as possible on test day.
Hello, I am Sam Smith, and this is Sam's MCAT Basics. This podcast covers the most important topics put out on the AAMC MCAT each year, and I determined this list by going through all the official practice materials that the AAMC puts out, and also some third-party practice material, and just put together this big list of topics that consistently kept on showing up, and ranked those topics and made podcasts out of it. So this podcast is going to cover atomic chemistry. And I'm going to talk about kind of 5 or 6 main topics within atomic chemistry. The first is going to be hybridization along with molecular geometry. I'll talk a bit about quantum numbers and quantum theory, and then go into electron configuration, periodic trends, and lastly, I will talk about atomic decay or nuclear decay. And, out of these topics, I would say the most important of these, or the one that I see most, is probably decay. You see decay a lot. You'll always get a hybridization question, probably, somewhere on the MCAT. And this podcast will really cover just the physics chem section of the MCAT. So it's just going to cover about 1 out of the 4 sections. Again, this is on atomic chemistry, and I hope it helps. All right, so I want to begin this lecture by talking about atomic orbitals. And these are somewhat confusing. If you had a similar intro chem class as I did, you got taught that atomic orbitals are these orbitals that electrons occupy, and they're kind of like planetary orbits in that these electrons orbit around the nucleus. The further out from the nucleus you get, corresponds to higher energy electrons. The furthest shell outwards is called the valence electron shell, and these electrons react with other atoms in order to form bonds. And in reality, that's not quite how atomic orbitals behave, or how they really look, I guess. So to have a better conceptual understanding of how these atomic orbitals look and behave, what I want you to do is forget that planetary model that is kind of BS that is taught in high schools and maybe even intro chem. I hope that your gen chem teacher kind of mentioned this. I want you to forget that for a sec. Think about an atom surrounded by a cloud of electrons instead. Think of this cloud as having different densities at different points away from the nucleus. Further, don't think about an electron as a little distinct point that lives somewhere outside the nucleus and zooms around in a circle or whatever it does. Just forget that for a second. All right, so now just know that quantum theory describes an electron as having both wave-like properties and particle-like properties. And together this is called the wave-particle duality of an electron. And essentially what quantum physicists did is they came up with equations describing where an electron lives around the nucleus. And these are called wave functions. And they can be used to determine the probability of an electron being found at any point outside of the nucleus. Now go back to that cloud that you're imagining around the nucleus. And all an atomic orbital really is just a probability cloud that surrounds this nucleus. So a higher probability of an electron being found at some point outside this nucleus is just corresponds to the density of this cloud, right? So the more dense this cloud is, the higher the probability that you will find an electron at that point. All right, so these probability clouds then have these distinct, very dense bands that kind of reside around the nucleus. And this is where electrons are more probable to reside. And so these actually correspond to the distances originally calculated by Niels Bohr, who actually came up with the classic mechanics version of nuclear orbitals, right? This planetary model that you've been taught. Niels Bohr came up with that. And so, right, that's kind of interesting. So you are more probable to find electrons in these actual distances in which we originally thought the electrons orbited around the nucleus. So compared to that original model, then quantum mechanics describes a continuous distribution instead of just saying that these electrons basically fit to these strict orbitals and they orbit around the nucleus and they just stick to these orbitals. What quantum tells us really is it's more of a distribution, more of a probability of electrons being found at certain distinct points around the nucleus. And it is important to note here that some of the places outside of the nucleus actually have a zero probability of an electron being found there. And so these show up as essentially holes in that cloud. And if you have no idea what I'm talking about, or you can't picture this in your head, go Google electron probability distribution or electron cloud probability distribution so you can kind of see what I'm talking about. But this kind of is a more realistic or quantum mechanics determined atomic orbital, than what you were introduced to in Gen Chem or maybe you have an idea of in terms of that planetary intergalactic BS. So then now that you have a little understanding of how atomic orbitals look, or maybe that confused you even more, let's get into the different kinds of orbitals, and we'll get a little deeper into quantum mechanics and what to know about quantum mechanics for the MCAT, right? You don't need to be a freaking physicist to be able to take the MCAT. You just need to have a few tools from the quantum mechanics set in order to really nail this down for the MCAT. So before I get into kind of the applications of quantum mechanics on the MCAT, let's briefly mention the shapes of the orbitals. There are 4 different atomic orbitals to know. There is the s orbital, the p orbital, the d orbital, and the f orbital. So if you remember from Gen Chem, the s orbital is spherical in shape, the p orbital is dumbbell shaped, and then the d orbital is kind of 4-leaf clover shaped. And then, you're at this point, your Gen Chem teacher may have gotten to the f orbital, and at this point they would say something like, "Don't worry about the f orbital. That is out of the scope of this class." Which also is the classic thing that professors tend to say when they don't know the answer to a question. But however, just know that the shapes of the f orbitals are actually out of the scope of the MCAT as well. So where are you going to see quantum mechanics and orbitals come up on the MCAT? Where there's 3 kind of main places that you'll see these come up. The first is in determining the electron configuration of an atom. There's a few exceptions to the common rules that I'll go over here as well. The second is in determining quantum numbers for a given electron. This is very similar to electron configuration, by the way. And lastly, you might see something about hybridization. And of course, as I said in the intro, hybridization tends to come up a lot, so I'll spend a good chunk of that discussion then going over hybridization. All right, so the first thing I want to talk about is electron configuration. So in atomic physics and quantum chemistry, the electron configuration is the distribution of electrons of an atom or a molecule. And this is that kind of annoying 1s2, 2s2, 2p6 notation. And what it does is it gives you an idea of the electronic makeup of what an atom is, or the electronic makeup of an atom. You can say, okay, this atom has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and so on. And so the most widespread application of electron configuration in real life is in the rationalization of chemical properties. So in order to understand how a atom is going to behave in a certain situation, a lot of times it really helps to know the electron configuration and the electron configuration of the surrounding molecules, and in that way you can kind of predict reactions. So in addition to the shape of an atomic orbital, again this is S, P, F, and D, there is also a number that describes the energy level of the orbital, and this is called the principal quantum number. And I'll talk about this in a little bit more detail when I get into quantum numbers. But for now, just know that this describes the energy level of a certain orbital. And so in order to complete these electron configuration problems, what you're going to want to do is you want to go look at the periodic table. And so the periodic table is actually broken down into orbital blocks. So the first block is the S block. The next block is the P or the D block, depending on where you're at on the periodic table. Then the last block is the F block. And each of these blocks is further broken down into principal quantum number energy levels. So this is, 1s, 2s, 3s, 4s, 5s, etc. And it's important to know that the D block starts at the third energy level, and the F block starts at the fourth. And so again, the D block is a lot of the transition metals. And if you have no idea what I'm talking about, please go look up a periodic table that has these blocks kind of highlighted so you can see what I'm talking about. The D block starts a little further down, and then the F block starts a little below that D block. And so what you do is you fill each orbital with electrons, starting at the lowest energy level and going to higher energy levels. And this is called the Aufbau Principle, the fact that you start filling orbitals at the lowest energy level. So the best way to do this is to have a periodic table in front of you, as you will on the MCAT. And what you do is you count horizontally across it, right? You start at the top, you start at the 1s orbital. You count 2 electrons there. You move over to the 2s, count 2 electrons there. And then next you move to the 2p, count 6 electrons there. Then you move on to the 3s, then the 3p, and so on. Of course, then eventually you get to the D block and the F block. But you just keep filling these orbitals, increasing in energy with electrons until you have the element of interest. So what do I mean by element of interest? Well, a lot of times on the MCAT, the questions will be, what is the electron configuration for fluorine? Or what is the electron configuration for nitrogen, right? It's going to ask you straight up to come up with the electron configuration. So that is going to be that's going to be the element of interest. All right, so I mentioned Aufbau's principle. You fill the lowest energy levels first. So what are the other principles in terms of electron configuration? Well, the next one I want to talk about is called Hund's rule. So Hund's rule says that electrons fill unoccupied orbitals first on the same energy level. In other words, electrons like to be alone unless they have to be doubled up, in the case where you have to go to a higher energy level in order to put more electrons in. And even when electrons are paired up, they have opposite spins, right? They don't even have the same spin. They're not the same electron. And so that is the Pauli exclusion principle, which says that no 2 electrons can have the same set of quantum numbers. And so as I'll get into, one of the quantum numbers is spin, so these electrons must have opposite spins. And this is represented by one arrow drawn up and one arrow drawn down. So one has spin up, one has spin down, essentially. And so how I like to think about this is the fact that I always had to share a room with my twin brother, right? So I have a twin, and because of that, we always grew up sharing a room. And, and that was because there was no more rooms in the house that I lived in order to spread out in, right? So that's like Hund's rule. If there's no more open spots in this certain energy level, then you pair up the electrons. If there's empty rooms, then each electron gets its own room. However, me and my brother shared a room, but we sure as hell didn't share the same bed, right? We didn't share the same bed. We had bunk beds. And so in the same way, 2 electrons that share the same orbital have opposite spins. So bunk beds, opposite spins, basically the same thing. On the MCAT, you're also likely to see electron configuration given in noble gas notation. And essentially what noble gas notation does is it condenses the electron configuration up to a certain noble gas into the abbreviation for that noble gas in brackets. And it's much more pleasing to the eye, and it gives you a better idea of the electrons of the outermost energy levels, the ones that you really care about in terms of reactions. And so to kind of summarize how to go about doing electron configuration, Number one, you fill the shell starting with the lowest energy, going up to the highest energy level. And you fill unoccupied orbitals at the same energy level. You fill all of those before pairing up electrons. And when you pair up electrons, you pair them up with different spins, opposite spins. And then lastly, you write these in noble gas notation by condensing the electron configuration to the closest noble gas, and then finishing the rest of the electron configuration up to that atom of interest. And please practice these. Like, you could hear me talk about it all you want, but if you don't put pen to paper and really practice these a few times, I bet, honestly, you could probably practice it once or twice. You see exactly what I'm talking about, and then that's it. But yeah, I think it's very important you actually practice a few problems. It's also worth mentioning that there are a few pretty big exceptions to this rule, and they have to do with the D block transition metals. Like the English language, there are some blatant exceptions, obviously, to these rules. And so the first is that a half-filled or fully filled D shell is more desirable than a filled S shell. So essentially what happens is elements that have 4 D block electrons tend to steal one from the S block, leaving a half-filled S block and a half-filled D block. Or, they might have 9 D block electrons, and they'll steal one to complete that D block and leave a half-filled S block. And Aufbau is probably rolling in his grave right now because this actually violates Aufbau's principle. So that's kind of the main one to know. Either a half-filled D block or a full-filled D block is more desirable than a filled S block. There's also some kind of random ones to know. You might memorize them, put them on your flashcards, whatever. I would say in terms of them being important, not that important, but it never hurts to really know as much as you can. And so the first is Nebidium, or NB, and it will actually have 1 S block electron and 4 D block electrons. So neither a full S or a full D. Then you have ruthenium, which is Ru, and it will have 7 D block electrons and 1 S block electron. Then you have rhodium, which will have 8 D block electrons, 1 S block electron. And then you'll have platinum, which actually has 1 S electron, 14 F electrons, which is a full F block, and then it will have 9 D electrons. So those are kind of the oddballs. There's more than that. That's kind of the ones I picked out, though. So yeah, just keep in mind that these rules don't hold up for all atoms, especially D block metals. All right, so that concludes the brief discussion on electron configuration. What I want to get into next is talking about the 4 quantum numbers. So what is a quantum number? So a quantum number essentially labels and describes each electron in an atom. As I said, the Pauli exclusion principle says that no 2 electrons can share the same 4 quantum numbers. In other words, an electron can be uniquely characterized by these 4 quantum numbers. If I give you each 4 quantum numbers, you can point at the electron it describes and say, that's the one right there, right? This is like first name, middle name, last name, birth date, right? You can identify pretty much anyone. There's not many overlaps if I give you all that information about someone. So you can think about it that way a little bit. All right, so again, there are 4 quantum numbers. The first is the principal quantum number, or N. The second is the angular momentum, or azimuthal quantum number, which is L. And then there is the magnetic quantum number, which is M sub L, which is M subscript L. And then fourth, there is the spin quantum number, which is M sub S, or M subscript S. And so the principal quantum number is the first one. And as I kind of briefly mentioned earlier, this describes the size or energy level of an atomic orbital, right? So an example here is, you have 1s, 2s, 3s, 4s, 5s, where that integer out front of the s orbital is the principal quantum number. The second quantum number is the azimuthal quantum number, and this has the abbreviation L. And so this describes the orbital angular momentum and shape of the subshell orbital. That's not very important to note. What's important to note is that L is the positive integers that are equal to or less than n minus 1. So let's just say you have a principal quantum number equal to 5. That means that the azimuthal quantum number then can be either 4, 3, 2, 1, or 0. The third quantum number is the magnetic quantum number, and this describes the orbitals available within the subshell, and this is defined as the integers between plus and minus L, including 0. So for instance, let's say that we have a L, or angular momentum quantum number, of 3. That means that our magnetic quantum numbers can be 3, 2, 1, 0, -1, 2, and 3. So again, the magnetic quantum number is just defined as the integers between plus and minus L, including 0. Lastly, we have the spin quantum number, or m sub s, and this is either plus 1/2 or minus 1/2, and it describes the spin of an electron. And by the way, just a little aside, this is not the actual spin around some axis, like how we think of the Earth spinning around its axis. But for the sake of the MCAT, you can imagine it if you want to, if that helps you remember that the spin number is plus or minus 1/2, whatever you need to do. And so, what do you really need to be able to understand, or what kind of questions are you going to actually see on the MCAT? For the most part, you'll see questions that will essentially ask you, which set of quantum numbers can actually describe an electron. And so most of the cases will be where they give you, an L that is greater than the N, which is not possible, or they'll give you a magnetic quantum number that is not some integer that's between plus L and minus L, right? Or maybe they'll give you a spin quantum number of plus 1. And so basically, it's being able to go through the quantum numbers and to cross out the ones that are not physically possible or are not possible. And so, like with these other problems, go through, do a couple practice problems, just understand the definitions of each of these quantum numbers and know which combinations are possible, know which combinations are not possible. Your L can't be greater than N, and your M sub L, which is the magnetic quantum number, cannot be greater than L, and it has to be an integer. And this can also include 0. So, just kind of some small things to remember. These problems should really be gimmies though, right? You just got to memorize these little rules and apply them. The last topic that I want to talk about under the umbrella category of quantum is hybridization. And so hybridization is the idea that atomic orbitals fuse to form these hybridized orbitals. And essentially, how scientists came up with this theory is that they observed that all the electrons in a bond have the same energy. And so this would only be the case if, for some reason, these orbitals formed hybrid orbitals when bonds were formed. So think about this. So carbon has 4 valent electrons. It has 1 valent electron in the 2s orbital and 3 in the 2p orbital. And on the other hand, hydrogen has 1 valent electron, and that is in the 1s orbital. So what is methane, right? Methane is CH4. So methane is 4 hydrogen bound to a carbon. If we just look at the energy levels of each of these orbitals, they're all at different energy levels. You have an electron that's in the 2s orbital, you have one that's in the 1s, and then you have electrons in the 2p orbital paired to electrons in the 1s. These are all at different energies. So then scientists kind of postulated that, all right, they must be forming some kind of hybrid orbital in which all the electrons are at equal energies within the bonds. All right, so now that I covered kind of a brief what is hybridization, let's talk about how this applies to questions on the MCAT. What the MCAT's going to do is they're going to give you some molecule, they'll give you the structure, and they will point to a certain atom or certain atoms, and they will say, tell me the hybridization of this atom. And it's actually quite simple how you solve these problems. First, identify the number of lone pairs and bonds that surround that atom. And don't forget to include bonds to hydrogen, right? Because these are often not shown in molecular drawings. Look at a benzene ring, for instance. They don't show any of the bonds to hydrogen. So don't forget the bonds to hydrogen. So what you do, you count up the number of lone pairs and the number of bonds. And then you have to realize that the exponents of the hybridization state have to add to the lone pairs plus the number of bonds. And remember that when a character doesn't have an exponent, that's an exponent of 1. So, for instance, you have the following hybrid orbitals. You have the sp orbital, you have sp2 hybrid orbitals, you have sp3 hybridization, sp3d hybridization, sp3d2, etc. And so, sp hybridized, you have an exponent of s1 p1, right? Because they don't have an exponent, so that's just an exponent of 1. So together, that means that sp orbitals have a sum of lone pairs plus bonds of 2. And then for sp2, you have s1 p2. That's a total of 3 lone pairs plus bonds. Then you have sp3, which is s1 p3, which is a total of 4. And so your lone pairs plus bonds must equal 4. So that's pretty easy, right? Go through, of course, do some practice problems, but the key to realize here is that the sum of the lone pairs plus the number of bonds on a certain atom must be equal to the exponents for the hybrid orbital. So sp, that is an exponent sum of 2, and therefore you must have a sum of 2 lone pairs and bonds to that certain atom. All right, the last thing I want to mention here is molecular geometry. And so what I originally did was I actually recorded kind of describing the different shapes, different geometries. But when I listen back to it, it's hard to visually kind of imagine as I'm saying it. So what I recommend here is that the geometries, the molecular geometries of these different configurations of atoms. Go look up a table, put it on note cards, whatever you have to do. Just know that that's important. I'm going to skip over it in this podcast and move on to the next topic, just because I didn't think it was very useful. But just know that that's something that is needed for the MCAT. All right, I want to talk about bonds now. So there's 2 different characterizations of bonds to know. There's the pi sigma characterization, which is based on orbital overlap. And then there is the ionic covalent bond characterization, and that's based on electronegativity. Let's talk about pi and sigma to start. So sigma bonds are formed by head-on overlapping atomic orbitals. So just imagine, take your fingers and make a pointer with one, make a pointer with other, overlap them. That is touch them. And, that's an inappropriate sign for something. If you don't know what, then good. But just also know that that's kind of how these head-on overlapping atomic orbitals look. That's essentially how they look. All right, so what about pi bonds? So pi bonds are formed by overlapping p orbitals. And it's important to note here that you need to have a sigma bond in order for a pi bond to occur. Imagine it being the case in which pi and sigma are dating, and pi is kind of that clingy boyfriend, sigma is that girlfriend who is just kind of free-spirited, does whatever the hell she wants, and pi gets a little jealous. He always wants to be around sigma, and therefore, he doesn't do anything unless sigma is there. You need to have a sigma bond in order for a pi bond to occur. So, a sigma bond must be formed prior to a pi bond forming. And so, how exactly does this work? Well, when a sigma bond forms, it puts p orbitals in close proximity to each other so that these pi bonds can form. And what's really important to know in these cases is the number of sigma bonds and the number of pi bonds in a single, double, and triple bond. So a single bond is one sigma bond, A double bond is a sigma and a pi bond, so one of each. And then a triple bond is one sigma and two pi bonds. And as I said, pi bonds are a bit stronger. And so you can see that this, as you increase from a single bond all the way up to a triple bond, you get an increased number of pi bonds. This is also why these bonds are increasing in strength as well, right? You know, a single bond is a little weaker than a double, which is a little weaker than a triple. On the other hand, bonds can be characterized as either ionic or covalent. So ionic bonds occur when an electron is essentially given from one atom to another, and then these species become charged and a bond occurs. And typically this is between a metal and a nonmetal. So, you know, sodium chloride, for example. Sodium gives an electron to chlorine. Chlorine has a negative charge now. Sodium has a positive, and they form this ionic bond. And so these bonds form through a redox reaction, right? An atom donates an electron and an atom receives an electron. This leads to a cation, anion, and these are electrostatically attracted to each other and they form a bond. And typically the electronegativity difference between atoms in order to form an ionic bond must be greater than 1.6. Covalent bonds, on the other hand, are when electrons are shared between two atoms. And this typically occurs between two nonmetals. And these are created from overlapping orbitals, which are what I talked about with the pi and the sigma bonds. And so there's a few different kinds of covalent bonds. The first is nonpolar covalent, and that is when atoms equally share electrons. And this occurs when two atoms have an electronegativity difference from 0 to 0.3. Then there's polar covalent. And so in polar covalent bonds, electrons are shared unequally. One atom is kind of hogging the electrons, taking the electrons from the other atom. And this occurs when there is an electronegativity difference between 0.3 and 1.6. And it's not really important to remember those electronegativity numbers. More important to understand conceptually what's going on. Ionic bond, you know, they're giving away the electrons, then you have this electrostatic charge that brings those two atoms together. Covalent bonds are just shared electrons between two atoms. All right, so that's a bit on quantum, as well as bond theory, as well as hybridization, which are all very interconnected subjects. Next thing I want to talk about is how to use the periodic table on the MCAT. So, you know, I think it's a common question as to when should I use the periodic table on the MCAT? My answer to that is periodically. No, when you really should use it is when you're trying to figure out trends or atomic trends, and this can be in terms of electronegativities, this can be in terms of atomic radii, this can be in terms of reactivity. A lot of different types of questions can really get at periodic trends. You know, it might be, what is the order of electronegativity of this set of atoms that I'm showing you? Or it can be, what is the order of increasing radii of the following atoms? So you'll see a few questions where this applies on the MCAT. So the first thing to know is what groups and what periods are on the periodic table. So groups are the columns on the periodic table, and periods are the rows on the periodic table. If you don't know what a column is, that's just going down. Periods are rows, and those are going across. And so groups, which again are going down, share physical and chemical properties. You know, for example, the very first group on the periodic table is the alkali earth metals, and they all react very violently with water. You can literally drop pure lithium, pure sodium, pure potassium into water, and you'll get these large, highly energetic reactions in which hydrogen gas is released. The next thing you'll want to know is where the metals, the nonmetals, and the metalloids are located on the periodic table. The metals essentially start at group 1. It's important to remember, though, hydrogen is a nonmetal. So excluding hydrogen, you start at the first group, and you go over to the 12th group. That's the end of the D block. And then you go over, one or two atoms in most cases, and those are the metals. And this is not too hard to remember. The kind of boundary of the metals in terms of where they stop and where the metalloids start is at aluminum, and then gallium, tin, and bismuth. So you can think everything to the left of those atoms is a metal, except for hydrogen. Don't forget that. The metalloids are between the nonmetals and the metals. This is boron, silicon, germanium, arsenic, and plutonium, among a few others. And just know that these have both the properties of metals and nonmetals. Lastly, you have the nonmetals. These make up the rest of the periodic table. This is carbon, nitrogen, oxygen, everything to the right of the metalloids. Another important group to point out is the very last group on the periodic table. These are the noble gases. They're known for their inability to react. They are very unreactive gases. All right, let's talk about periodic trends. These are the most important thing to know, I think, in terms of the periodic table. So there are 4 different things to know here. Number 1 is atomic radius, electronegativity, electron affinity, and ionization energy. These are not too hard to remember. What you got to know is that electronegativity, electron affinity, and ionization energy all increase from left to right and down to up on the periodic table. That means that fluorine is the most electronegative atom, and francium is the least electronegative, has the lowest electron affinity and the lowest ionization energy. On the other hand, atomic radius is a property that trends the opposite direction. So atomic radius increases from right to left and up to down, meaning that fluorine has the smallest atomic radius, while francium has the largest atomic radius. Just an important aside, atomic radius changes with ionization states. So let's say that an atom loses an electron and becomes ionized. Take the example of sodium. So sodium likes to become +1, therefore losing an electron to become positively charged. So what happens is now you have the same amount of positive charge in the nucleus, but you lose an electron. So the radius actually goes down because now you have a larger effective charge that pulls each of these electrons. Right? Each of these electrons feels a little bit more of a positive charge because you essentially watered down the number of electrons in that atom. On the other hand, if you have something like chlorine that likes to gain 1 electron to become negatively charged, then you actually are increasing the atomic radius when this atom accepts an electron. All right, so that's a little bit on the periodic trends that you'll see on the MCAT. The big key here is that you need to be able to order different elements in terms of their atomic radii, their ionization energy, electronegativity, and everything. Those should be pretty easy, right? Easy to remember that the only trend that is increasing from right to left and up to down is atomic radius. The other trends increase the opposite direction. Also, don't forget what a group and a period is. I've seen that a few times. You might also see something like, what kind of properties does this element have here? And, the answers will be either metallic properties or non-metallic properties. And therefore, you will need to know, all right, are we talking about a metal? Are we talking about a non-metal? And so an easy way to do that is be able to tell on the periodic table where the metals are, the non-metals are, and where the metalloids are. The last thing I want to discuss is nuclear decay. All right, so there are 2 different things I'm going to mention in terms of radioactive decay. The first is half-life, and the second is introducing a few different kinds of radioactive decay. So, radioactive decay is the decay of particles within the nucleus over time, and this follows an exponential decay model. If you don't know what exponential decay looks like, I recommend just going and Googling that and seeing kind of what it looks like. Always important on the MCAT to be able to recognize different kinds of graphs in terms of, what's linear, what is exponential growth, exponential decay, what is a quadratic look like, etc. Or what does a plot of a log look like? A term you will see quite a bit on the MCAT is half-life. In the terms of decay, half-life is the time for 1/2 of a given substance to decay. And so typically you will ask to either solve for the half-life of some kind of radioactive compound, or you will be asked how much of a compound is left after it undergoes X amount of half-lives. And so the equation that governs exponential decay is some amount of substance at time t is equal to the initial amount of that substance times e to the minus kt, where k is the exponential constant and t is the time. So how do you use this equation to solve problems? Well, a lot of times they'll give you the half-life of whatever decaying substance you have. And so they'll say, for instance, carbon-14 has a half-life of 5,000 years. And you start out with 12.5 milligrams. Okay, cool. Well, now you plug in 12.5 for your initial amount of substance. And you know that half of that is present after one half-life. So you plug in 12.5 divided by 2, which is 6.25. And then you plug in 5,000 for T, and then you can just go back and solve for K. So that's pretty easy. However, I've seen a lot more problems that will ask you to find the amount of a substance left after, 4 half-lives or 5 half-lives. And so, yes, you could use the equation. You could plug in everything solve for K, then go back and solve this problem. The easier way to do it, though, is to just divide 12 by 2, divide 6.25 by 2, divide that by 2, divide that by 2 4 times, and that is the amount you're going to have after 4 half-lives, right? That's a lot easier than going back and using this equation. So a lot of times what I'll do is I'll kind of do that the shorthand way where I just divide by 2 until I get to, the amount after X amount of half-lives, or, it might ask, it might say something like you start with 12.5 milligrams and you now measure the sample to have 0.8 milligrams of, carbon-14 that's been decaying. Well, then they might ask you, okay, how many half-lives has this undergone? And you can use the exact same process, right? So you start with 12, you just divide by 2, and, count how many times you divide by 2 until you get to 0.8 or until you get to about 0.8. And that's 4 half-lives. So that's just a kind of a shorthand way to do it without using the equation. Of course, sometimes you will have to use the equation. But yeah, these half-life problems show up quite a bit. All right, so the next important thing to understand are the different types of radioactive decay. The first is alpha decay. The second is beta decay. And there's a bunch of different types of beta decay. And then there's gamma decay. These are kind of the 3 main types to know. So alpha decay is the emission of an alpha particle. That is 2 protons and 2 neutrons. So then alpha decay decreases the number of protons and neutrons of some atom. So for example, we have radium, which has 88 protons and a mass number of 226, meaning that it has 138 neutrons. So what happens is you lose this alpha particle, which is also a helium nucleus, and this converts radium into Rn, which I'm not sure what element that is, but it's Rn. And again, so you lose 2 protons, 2 neutrons, so that decreases the atomic mass number from 226 to 222, and you lose 2 protons, so the atomic number changes from 88 to 86. In other words, this kind of decay actually changes the atom. All right, so the next kind of decay I'm going to talk about is called beta decay. And there's 3 different types I'm going to talk about. I'm going to talk about beta minus decay, beta positive decay, and then I'm going to talk about electron capture. So in beta minus decay, the atom emits an electron and a neutron is converted to a proton. In other words, this increases the atomic number by 1 and does not change the atomic mass number. In beta positive decay, on the other hand, you emit a positron and you have a proton converted to a neutron. So you actually decrease the atomic number by 1 while keeping the atomic mass constant in beta positive decay. On the other hand, in electron capture, you gain an electron or you absorb an electron and a proton is converted to a neutron. And you can kind of think of this as when you capture an electron that collides with a proton and you have a negative charge and a positive charge that combine to create something that is a neutral charge, aka a neutron. I don't think that's actually how it works, but that's how I like to think of it just to kind of memorize it. And so in other words, what does this do to an element? Well, you convert a proton to a neutron, and so you are decreasing the atomic number by 1, which is very similar to what beta positive decay. All right, and the last form of radioactive decay I want to talk about is gamma decay. So gamma decay is just the emission of a high frequency photon. And this has no effect on either the number of protons or the number of Jimmy neutrons that are in an atom. So in other words, it really don't do shit. All right, so that's that for decay. I hope this helps you memorize the different kinds of decay, helps you kind of sort them out in your mind. Just know that it's important. You will likely see a question about this on the MCAT. All right, so this concludes the podcast on atomic chemistry. And truth be told, originally in this podcast, I had that same noise and effect on every time I said atomic chemistry. And as I was listening back to it, it just was kind of annoying. So I took that out, except for the first and the last. But anyways, I hope this podcast helped. This is some pretty important stuff. Kind of boring, yes, but also important. Thanks for listening. I hope you listen to the next one. Go ahead and rate us, review us on iTunes if you really liked it, if you really think this helps. All right, and now for a segment I call the MCAT Advice of the Day. So this really applies if you're just now thinking about starting to study or, just starting to study and kind of wondering, am I doing this right? Is this really how I should be doing it? Right? Because you're probably going to put in a lot of effort and you want to make sure you're doing it the right way. So what I recommend is you go talk to friends, talk to acquaintances, people you know that have taken the MCAT and done well. Get advice from them. Someone who's been through it all, really kind of knows what's going on or the best ways to study. And if you don't have anybody that you know or close relationships with, whatever, that have taken the MCAT, go look up some forums online. Go to Reddit, go to studentdoctor.net, and kind of read some of the blog posts people have posted that have done really well in the MCAT. And a lot of times they post how they study. So that's something I think is kind of important. Get advice, seek advice on how to best study for the MCAT. And I guess that really goes for a lot of different things in life, right? You want to find mentors that'll help you. So that's my advice.
Each episode of MCAT Basics is brought to you by Med School Coach. To access Med School Coach services, including MCAT tutoring and medical school admissions advising, visit our website at medschoolcoach.com. Good luck as you prepare for the MCAT, and we hope you tune in again next time.
Come on, Murph. I'm trying to podcast over here, dude.